Hey guys, so in this video we're going to start talking about the conservation of angular momentum. Let's check it out. So remember that when we talked about linear momentum, that the most important part about linear momentum was the fact that it was conserved, or that it is conserved, right? It's conserved in certain situations. We'll talk about that in just a bit. The same thing is going to happen for angular momentum. Most angular momentum problems are actually going to be about the conservation of angular momentum. So they're going to be about conservation. They're going to be conservation problems. Okay? So what I want to do here is do sort of a compare and contrast between linear momentum and its angular equivalent, angular momentum. So linear momentum, little p, is mass times velocity. Angular momentum, big L, is I omega, moments of inertia, and angular speed. Linear momentum is conserved if there are no external forces. And angular momentum is conserved if there are no external torques, right? And this should make sense. Angular momentum is the rotational equivalent of linear momentum. Torques is the rotational equivalent of forces. Now, even better description is it's actually not that there are no forces. It's just that there are no external forces, or that if there are external forces, they at least cancel each other out. So an even better definition is if the sum of external forces, again, they could exist, they just have to add up to zero. Same thing here, the sum of the external torques has to be zero. This is the condition for conservation of linear momentum and the conservation of angular momentum. And in the vast majority of physics problems, those quantities are conserved. Certainly, all the problems we're going to look into from now on for angular momentum will have conservation. All right. One difference between these is that most problems for linear momentum involve two objects. Pretty much all of them involve two objects colliding against each other. Okay, so the conservation equation will look like this: P initial equals P final, right? So it's saying that momentum doesn't change. This is of the system. So I can expand this equation, and I have two objects, so P initial becomes P initial 1 plus P initial 2 equals P initial 1 plus P initial 2. So it's going to be this very familiar equation. M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. Now, angular momentum is a little bit different. That there's a lot of angular momentum problems that involve just a single object, right? So the most classic, probably the most classic angular momentum, conservation of angular momentum question is when you have an ice skater. So let's say you have a girl ice skating and she is spinning with her arms open, and she closes her arms and she's going to spin faster. This is a conservation of angular momentum question. We're going to solve this later. And it's just one object. It's one body that's spinning, okay? Now, the conservation equation will be similar. I'm going to have that L initial equals L final, right? Because L doesn't change. That's the whole deal. And L is I omega. So I'm going to say that I initial, omega initial, is not going to change. It's a constant, okay? But what I want to do here is I want to expand this equation a little bit to show you something. So moment of inertia, I, for a point mass, is something like mr squared. For a shape, it's something like, let's say for a solid cylinder, it would be half mr squared. For another object, for like a solid sphere, it would be 2/5 mr squared. The point that I want to make here is that it's something mr squared, right? What changes is that here you have half, here you have 2/5. Here there's like a 1 that hides in there, right? That's implicit, we don't have to write. So I'm going to say that this takes the shape, this I, takes the shape of box, which is some fraction, mr squared. And then I have omega. So I'm just expanding I omega to show you this. And I'm going to say that this is a constant. This is a constant. Okay? Meaning this number doesn't change. So really, the kinds of problems you're going to have, there's two basic types of problems. In one type, the mass will change. I'm going to put a little delta here on top of m. The mass will change, which will cause a change in omega. On the other type of problem, the r will change and cause the change in omega. So if the mass of a system changes, the system will slow down, right? You might be able to see here, if this mass grows, the system will slow down. Or if the radius of the system, the effective total radius of the system increases, then the mass, the velocity of rotation will go down as well. So the opposite case of what I just mentioned with the girl spinning is if she's spinning like this, and then she opens her arms, she slows down. And that's because her total R, right? You can see that these things are going away from the axis of rotation. So the R grows, therefore the omega becomes smaller, okay? So the two types of changes we're gonna have for one object is that either M or R will change, and those will cause a change in omega, okay? Change in omega. Now, when we have two objects, we have problems where you're essentially adding or removing mass. So the classic example here is there's a disk that's spinning, you add a little block to it, what happens? Well, the disk's now gonna spin a little bit slower, and we can calculate that, okay? When we had linear momentum, the two big groups of problems we had were push-away problems, where two things would, like when you shoot a gun, the bullet goes this way, the gun goes this way, or collision problems. So push away, two things are going away from each other. Collision, two things are coming into each other. Okay, and we also had these types of problems where you're adding or removing a mass, in linear motion. Which, if you think about it, adding a mass is a collision, right? One mass joins the other, and removing a mass is really a push-away problem. Is if you jump out of a skate or something. All right. So anyway, that's it for that. I have an introductory example here talking about a bunch of different situations so we can discuss what happens in these situations. And we want to figure out whether the angular speed omega will increase or decrease. All right, so an ice skater, we just mentioned this, an ice skater spins in frictionless ice. What happens to her angular momentum if she closes her arms? If you close your arms, you spin faster. You might know this from class, from just watching TV, from doing it yourself, or we're going to use the equation here. So what I'm going to do is I'm going to say L is a constant. L, which is I omega, is a constant. I'm going to expand I omega into something mr squared omega, and this is a constant. I'm just going to write C. And look, what's happening here is that by closing her arms, her R is decreasing, therefore her omega is going to increase. So the answer is that omega increases. Omega will increase. All right, B, a large horizontal disk spins around itself. What happens to disk's angular speed if you land on it? So there's a disk spinning around itself like this. You land on it right here. So this is you. You got added to the disk. What happens to the disk's speed? Well, I equals I omega is constant. I'm going to expand I omega to be something mr squared, okay, times omega. I mr squared times omega is a constant. What's happening here is there's mass being added to the system, therefore the system will slow down. So I'm going to write here that omega will decrease. All right. C. An object is tied to a point via a string that spins horizontally around it. So here's an object, and it's tied to a point here. It's connected by a string, and it's going to spin horizontally around the string. So an object is going like this because it's connected to a string. And what we want to know is what happens if you shorten the string. So again, I equals I omega is a constant. C, I omega I'm going to expand to be something mr squared. It doesn't matter what this something is for these problems. We're just doing a quick analysis of what would happen. If you shorten the string, if you shorten the length of the string, you're shortening the radius of rotation of this object. Therefore, the omega will increase. Omega increases. Okay. You can imagine that if you spin something on a really long cable, the second you pull the cable in, it's going to then, instead of spinning like this, it's going to get faster like this. Okay. And then the last one, a star like the sun spins around itself. Cool. And I want to know what happens if it collapses and loses half of its mass and half of its radius. Okay, so you might know this, you may know this, stars live for obviously billions of years. Eventually they run out of star fuel and they collapse. And what that means is that they're going to significantly shrink in size, in volume, and in mass. Okay, so that's going to happen to our sun like in 10 billion years. You're safe, don't worry. So what happens if it collapses and loses half of its mass and half of its radius? So L equals I omega C. It's an object that spins, but it's not going to, its angular momentum is conserved even though this thing is blowing up, right? So I have, this is going to be something mr squared omega, and that's a constant. So here we actually have precise numbers, half and half. So if this goes down by a factor of 2, get that, and then this goes down by a factor of 2. Notice that r is squared, so I'm going to actually square the factor of 2. Let me get out of the way. So the net result of this going down by a factor of 2 is that it actually goes down by, the whole thing goes down by a factor of 4. So I have this going down by a factor of 2, this going down by a factor of 4. I multiply those two, and I have this thing growing by a factor of 8. Okay, so 2 times 4 is 8. If these two variables here become 8 times smaller, this variable has to become 8 times greater, so that the whole thing is a constant. So this star would then spin 8 times faster than it was before it collapsed. Okay. So that's it for this one. Some introduction in terms of what to expect in these different kinds of problems. We're going to solve most of these later on. But that's it. Let me know if you have any questions, and let's get going.